Morning, calculus students. Sorry about that last time. There's something that I didn't explain it clearly. And here's the continuation with section 7.4, integrated by partial fractions. So now we get into more complicated examples. So let's say that we do have this type of integrand. So it's the same power, top and the bottom. So what we can do first, we can start it with the long division process. So the degree of the numerator is not less than the degree of the denominator, so we perform the long division. And then we come up with 1 plus x minus 1 over 4x squared minus 4x plus 3. Okay, so let me just put it this way. Okay, so now notice that the quadratic 4x squared minus 4x plus 3, it's irreducible because that it's discriminant. B squared minus 4ac is a negative number, so it's less than zeros. So this means it cannot be factored. So we don't need to use the partial fraction technique. So anytime that you see something like the denominator which is not factorable, so most likely we don't have to use the integration by partial fractions technique. Okay, so instead of doing that, we try to complete the square for this. So for the quadratic, so we do end up with 2x minus 1, the quantity of 2x minus 1, quantity square plus 2. Again, anytime you complete the square, you want to isolate the constant. So the way to find out the number, so always take out the greatest common factor, and then using that b over 2 form, b over 2 quantity square, so we can get a number at. And then, so you can factor it, so complete the square, so you end up with this. So instead of using that integration by partial fraction technique, so we're using the u substitution for this. So obviously for the inner function, we do have 2x minus 1, so then du would be 2 dx. And also solving x here, so we do have 1/2 times the quantity of u plus 1, because that by the time you plug in back to the original integrand, so you need to solve for x in terms of u. So now we'll look at that the derivation here. So once we do the long division, we end up with this, and then using the u substitution again. So this one can be written as u squared plus 2, because once we complete the square for that, the constant 2 just isolate it, and then that 2x minus 1, so we just put it as u, and then solve for x. We do end up with 1/2 times the quantity of u plus 1, and then minus 1, we just want to carry along with the constant. And then instead of using dx, we're using du. So missing element, we multiply that outside and then inside. So 1/2 du, which is dx. And now for the rest of this, we just want to integrate it. So integrals of 1, which is x. And then integrals of this whole quantity here. So try to simplify it a little bit first. So we do have u minus 1 over the quantity of u squared plus 2. So 1/2 times 1/2, that just gives you 1/4. It's a coefficient. We can always put it out. And now for the next step here, so we try to separate the terms. So instead of using that u minus 1 all within the same denominator, we just separate them out. So we do have u over u squared plus 2. And then the other one is minus 1 over u squared plus 2. But don't forget to distribute the 1/4 because that's the greatest common factor, or it's a leading coefficient. And then integrate it. So this pattern here, it shows that it's the natural log of u squared plus 2, because that 2u, and then that'll be the derivative of u squared using the chain rule, or you can use that the other w substitution. And then over here, so we do have an inverse of tangent of u over root 2. So this one is the pattern of the inverse of the tangent functions for the integral. And then 1/4 times the missing element, 1 over root 2. And then don't forget to add the constant c at the end, because that's the indefinite integral. And the last step that you need to finish, so don't forget about the unsubstitution. So u, which is written as, the u substitution we set up earlier, 2x minus 1, you want to expand it and then combine the like term. And then this one too, so 2x minus 1, so just replace that u with that 2x minus 1. And then everything else, just multiply them straight across, the fractions, numerator, denominator, and the constant c, just bring it down to the bottom. And that's for example 6. Okay, so now let's see what else that we have for the rest of this. So for this example, once again, so it illustrates the general procedure for integrating partial fraction of the form. So where b squared minus 4ac, it's less than 0. If you see anything like that, so that means you want to complete the square. So you don't need to do it with the integration by partial fraction technique. And also once you complete the square for that one, you can always separate them. And then you can integrate it each term individually. And now let's talk about case 4. So let's say that q of x contains a repeating irreducible quadratic factor. So let's say that q of x has the factor of the quantity ax squared plus bx plus c to the power of r, and where that b squared minus 4ac it's less than 0. So let's say we do have the repeating factor, irreducible repeating factor. Okay? So now here's the one. So according to the denominator, we do have x minus 1. So we do have linear and not a linear factor. And then the quadratic. So the quadratic factor here, it's irreducible. Another irreducible quadratic factor, and also it's considered repeating because the power is from 1 and then all the way to the third power. So the way that we deal with this, so we need to use the decomposing partial fraction. So started off with that a over x, and then b over x minus 1, because those are the linear, doesn't matter, linear binomial, monomial, we just put one letter on top of it. And then for the quadratic trinomial, then this one for the top, you need to put in the linear binomial, because at the top part, it's always one term less compared to the number of terms down the bottom. Again, one more time, whatever the number of terms that you have for the denominator, it determines the number of terms that you need to put on the top. If that's a quadratic trinomial, so that means the top part got to be 1 degree less, and also got to be one term less. So it's a linear binomial. And then this one right here, if that's a quadratic binomial, the top part, it's still considered a binomial, but it's a linear binomial. Okay, so you need to do the matching. So if that's one term, linear, so the top part is just one constant term. If that's a quadratic, the top part got to be linear, and it's a binomial. And now, what about for the repeating factor? So for the repeating factor, so the next one, it's also considered linear. Well, this one is a quadratic repeating factor with the quadratic binomial. So the top part, we need to put in the linear binomial. And then for the cubic repeating factor, the binomial, so the top part, we put in another linear binomial. Okay, so now for this one, so once you do the partial fraction decomposing, you want to solve for a, b, c, d, e, f, all the letter, g, h, I, and j. Okay, so that's one of those examples. So try to do it that way, so it's going to be a lot of things that we need to solve. But now let's take a look at that, the other problem here. So let's say we do have another irreducible repeating quadratic factor. So linear, so it's a over x. Binomials, quadratic, so the top part we put in bx plus c. And then the repeating factor, irreducible quadratic factor, so we put in dx plus e on top of it. And then once you multiply it out, multiply the missing element, try to expand it, and then we want to group those like terms. So the x to the power 4, okay, so the one with the fourth power term, we want to group those coefficients together. The one with the cubic power, we want to group those coefficients together. Quadratic, so on and so forth, we just want to group those like terms together. The purpose of doing that, we want to set up the equation for the linear coefficients, and also the linear coefficients, and also the quadratic coefficient, and also the cubic coefficient. So for the 4 degree, so there's no 4 degree for the numerator, so that way we just can set that a plus b equals 0. So for c, obviously it's negative 1. And then for 2a plus b plus d, compared to the power term here, so that the whole thing here, so that equals 2. And then for the linear term, we do have c plus e, so that equals negative 1. And then constant a, obviously is the constant, which is 1. So this one is just like a matching. So once we find out the like group, so we can just compare the coefficient along with the letters. So here's what we found. And then solving for a, b, c, d, and e using linear system equations. So we can just find out those values. And then just plugging those numbers back to the setup for the integral and then the integrand. So we can separate those terms out. So we do have integrals of dx over x, integrals of x over x squared plus 1, and then minus, okay, minus because that negative sign, distribute. So dx over x squared plus 1, and then the last term, that just consider x over the quantity of x squared plus 1 square. And then integrating it, so integrals of 1 over x, obviously it's a natural log of absolute value of x according to the formula. And then this one is similar, so natural log of x squared plus 1 by using the u substitution if you want to do that. And this one is also pretty obvious. It's inverse of tangent of x. And then for the last term, if you try to using that the u substitution, we're using u as x squared plus 1. And then we found that it's negative 1 over 2 times the quantity of x squared plus 1 square. And then constant k, it's just like the constant c, it's a family c, it's the indefinite integral. So that's why we need to carry the extra constant down to the bottom. So we know that sometimes partial fraction can be avoided when integrating a rational function. Okay, so something like this. So this one could be evaluated by method of case 3, so the video that I put up earlier. So this one, using the u substitution, we found that u can be written as x to the power of 3 plus 3x if you try to distribute the denominator. And then du will be considered 3x squared plus 3 times dx. So take the derivative and then put in that dx, taking that derivative implicitly. And then, so this one can be found by using the u substitution, so integrating it. So we do have 1/3 natural log of absolute value of x to the power of 3 plus 3x plus constant c. And some non-rational functions can be changed into rational function by means of appropriate substitution. So we can always change that like and root of g of x. So we can use that to use substitutions. So that might be a little bit more effective. Okay, so let's say we do have something like this. So integrals of square root of x plus 4 over x dx. So this one, a lot of people might be saying that x is just u, but if you try to use that, this one, it's meaningless by using the u substitution. So anytime that you try to use the u substitution, it's either making the integrand simpler or making more, things that can be reduced or can be factored. So here's what we found. So let u equals the top, square root of x plus 4. And then solve for u, solve for x in terms of u. So we square both sides, and then we isolate that x by itself. So x will be u squared minus 4. And then dx, taking the derivative both sides implicitly. So we do have dx equals 2u times du. And then with all the substitutions, so we put in this. So it's u over u squared minus 4 times du times 2u. And then this one, just multiply the numerator straight across. And then we just want to use the long division process, divide it, separate them out. So the quotient, it's 1, and then the remainder, so then that would be considered 4 over u squared. And then minus 4. Okay, so integrating it individually. And also, we can evaluate this integral by factoring u squared minus 4. You want to do it that way. And then you have to use the partial fraction technique. So separating them out, and then we do have integrals of du times 2, so then that would be 2u. Integrals of du over u squared minus 4, and that one to just consider a times 1/4, which is 2. And then natural log of absolute value of u minus 2 over u plus 2. And then the last part right here, you want to unsubstitute. Again, don't forget to bring down the family c. Okay, so thank you for watching the video today. So any questions, comments, so just put up on the YouTube channel. And I'll see you guys next time. Ciao.